We began our survey of elementary function types with looking at linear functions. And linear functions, well, why do we start here? Well, because these are probably the simplest kind of function that we can think of, probably the first one you ever encountered. And they also are the most important class of functions. They have a very special place in the study of calculus for a number of reasons. One, because they're very useful to model real-world phenomena. And they're also just because they're a simple class of function to look at. But many real-world things actually are modeled quite well with linear functions. And it turns out that if a function is differentiable, which we'll worry about in our next unit, then when you zoom in close on the function, it looks very close to a linear function. So many functions for short periods of time can be modeled very well by linear functions, or at least approximated well with linear functions. So linear functions have this very special place in our study of functions. So let's look at them. The simplest kind of linear function is a constant function. In fact, the simplest kind of function, period, where the formula is f of x equals k for some real constant number k. And so we're going to prove that these are constant functions are actually continuous. So given any epsilon greater than 0, let delta be epsilon for any real number c. If x is between c minus delta and c plus delta, then we see that f of x minus epsilon is just k minus epsilon. And that's certainly less than k, which is f of x, which is certainly less than k plus epsilon, which is just f of c plus epsilon. And I probably should have said f of c here, but it really doesn't make any difference because f of x is the same thing for every value of x. And in fact, in this particular case, we didn't even mention delta at all, because really, for any number you pick, notice there's no mention of delta here, that k is between k minus epsilon and k plus epsilon. It doesn't matter what x it is. It doesn't have to be between any particular values of c minus delta and c plus delta. So, very simple, kind of boring function, actually. For an example, f of x equals 2.5, the graph we see there in the table here. So notice that the graph is a horizontal, solid, straight line. And the table is a table where we can put anything we want in the x's, and of course all the y's are the same value, whatever the value is here. So very simple, very easy to go from formula to table to graph, or table to graph to formula, or start with any one of these three and get the other two. Okay, well, so the next one I want to look at is the identity function f of x equals x. And so that's a very specific straight line when you look at the graph. It's a solid line going through 0, 0, 1, 1, 2, 2, and so forth. So all the x and y values are the same. So if you look at a table here, if you think about it as a function is transforming an input into an output, this is the function that doesn't do anything. It just leaves the input alone, and it is the same as the output. So let's prove that it's continuous. Given any epsilon greater than 0, let delta be epsilon for any number c that's a real number. If x is between c minus delta and c plus delta, then f of c minus epsilon is c minus delta, because f of c is c, epsilon is delta. And we know that c minus delta is less than f of x, which is c, right? And then we know that c, of course, is less than c plus delta, but c plus delta is c is f of c, and delta is epsilon. So we've got f of x in the middle between f of c minus epsilon and f of c plus epsilon. And so, and of course the function is defined there, f of c makes sense. So this in fact proves that f of c is the limit, and that f of c actually exists, so that makes this a continuous function. So the alternate definition of continuity says that if you can get f of x between f of c minus epsilon and f of c plus epsilon for all x's that are between c minus delta and c plus delta, then you prove that it's continuous there. And notice this is true for any real number we pick for C, so this is actually a continuous function with the domain of all real numbers. So it's a line, has slope 1. So it turns out that if we just know these two little simple functions, a constant function is continuous and the identity function is continuous, we can just leverage those two things along with limit rules to actually turn out to get lots of functions are continuous. And so we've already got some rules about continuous functions. We can actually prove all kinds of things here are continuous. So for example, linear functions. In general, linear functions have the formula f of x equals mx plus b, where m and b are constants. 0b is the y-intercept. Actually, I really kind of prefer to use y sub 0 instead of b there because it is the y-coordinate when x is 0, but I'll leave it like this for right now. And m is the slope. Okay. Now, we want to prove that f of x equals mx plus b is a continuous function. Now, I'm going to do two proofs. First one is going to be a sort of a direct proof to actually prove that the limit is actually f of c. And then the second one, we'll use some of our properties that we've already proved. So the first proof says if we've given any epsilon greater than 0, let delta be epsilon over m. We discussed earlier in a video why this would be the appropriate choice for delta. And you'll see that it works out here in the proof. For any real number c that we pick, if x is between c minus delta and c plus delta, then c minus delta is less than x, which is less than c plus delta. But delta is epsilon over m. Okay. Now, let's see what we can do. We want to transform the middle into our f of x. So we want to multiply by m on all three sides. So that makes the middle into mx. When we multiply by m on the left, we distribute and we get mc minus epsilon. And we distribute on the right, we get mc plus epsilon. Now we add the b to all three parts to get mx plus b in the middle. And that gets mc plus b here and mc plus b here, plus epsilon on the right, minus epsilon on the left. mc plus b then is f of c, both here and here, and we see that we've sandwiched f of x in between f of c minus epsilon and f of c plus epsilon. And of course f of c is defined. This makes this f of c the limit, and it makes, therefore, by definition, this function is continuous. So all linear proofs can basically follow this format. Actually, we just proved all these limits for all linear functions once and for all here. Now, another way to do this, because of our previous results, is to do a proof this way, maybe a simpler proof. Since y equals x is continuous, so by properties of continuity, we know that a constant times a continuous function is continuous, so y equals m times x is continuous. Again, for any real number m. And again, by the properties of continuity, we know that the sum of two continuous functions is continuous, and b is a continuous function. A constant function is continuous. So we needed the fact that we built that up out of the fact that we knew that we started with the identity function is continuous, a constant function is continuous, y equals b is continuous, and the sum of two continuous functions is continuous. And so that builds that up. So what does a graph look like for a linear function? Of course, they're named after the graph. The graph is a line, a solid straight line, if we want to be kind of redundant there and emphasize that. So another thing that you'll see on the graph is moving to the right one on the graph moves the y values vertically by m units, whatever m is. M is the slope. And that's from any point on the graph. Another recursive pattern that you can see in the y values here in the table is adding 1 to x results in adding m to y. So that is f of x plus 1 is f of x, and then plus m. In the table, equal changes in x result in equal changes in y's, and specifically, well, so that says if the x's are evenly spaced out, we just add a constant each time to find the next y. Specifically, we have that recursive pattern, adding 1 to x results in adding m to y. Now, if the m is positive, so a positive slope says the function is increasing, and a negative slope says the function is decreasing. If m is 0, then this reduces to a constant function, and of course that is a constant. So here's for example, if m is greater than 0, if we look at the m behavior, you take the limit as x goes to infinity, it increases without bound. So it goes to infinity. If as x goes to negative infinity, we go way out the left, it goes down forever. But of course, if the slope is negative, it reverses. So as we go, the limit as you go to infinity is negative infinity, and the limit as you go to negative infinity is positive infinity. Of course, that means it doesn't have limits on the ends. It doesn't even have ends, really. The most important thing is we look at the rate of change. The rate of change is the slope. That is delta y over delta x, or y2 minus y1 over x2 minus x1 between 2 points, x1, y1, and x2, y2. That slope is a constant. And so the most important thing you want to remember about linear functions is linear functions have a constant rate of change, a constant slope. Here's an example where we see some of these things, and we can see the structure here. F of x equals 2x plus 1. We see that when you plug in 0, you get y is 1. So 0, 1 is the y-intercept. You can see that in the table right here. You can also see that in the graph right here, where we see it crossing the y-axis at 0, 1. Okay. This is, let me show you one more thing. This is what's called the slope y-intercept form, or just the slope intercept form. Okay, we can also have a slope x-intercept form. Okay. Sometimes that's useful to look at there. The slope x-intercept form is like this. It's a factored form. And so we simply factor out the m and what we end up with is, let me write it this way, say minus x sub 0. And so x sub 0 then is our x-intercept. Okay, well, it's the x-coordinate of the x-intercept. And again, m is the slope, and it looks like this. Instead of this being, of course, where 0b or 0y sub 0 is the y-intercept, here this time we have an x-intercept, so the y is 0, and the x is this x sub 0. And that's going to be the x-intercept. So that's the other useful form. So there's really two main useful forms. This form here, where it's sort of expanded out, which is the kind of the standard form. That's the slope intercept form, or the slope y-intercept form. And then we have this other form here where we factor out the slope, and then you can see the x-intercept on that one. So let's see if we take this one here. Let's see, that would be equals 2 times x plus 1/2. Okay, and so we would see that's in the factored form, or 2 equals x, 2 times x minus a negative 1/2. So we see that negative 1/2, 0, is the x-intercept right there, and we see it there. Okay. Another way, of course, we see this as a straight line. We see the positive slope, so it's increasing, goes out to infinity on the right, down to negative infinity on the left, goes from negative infinity to positive infinity on the x's. We can put in whatever we want. Here I've gone up by 1 on the x's. If you go up by 1 on the x's, notice that the y's, there's our 0, 1 there on the where it starts on the y-axis. And then from there, when we go up 1 on the x, we go up 2 on the y. So notice that we have a common difference here of 2, and that's our slope. Okay, I think that's a quick overview of linear functions. For more information about linear functions, I refer you back to my notes on that in my videos on linear functions. I have a whole bunch of information about that, covering this in much more detail.